Find the design strength of the steel member in pounds. In this problem, a steel member is subjected to a force P. Certain dimensions of the member are provided to show the locations of the 4 bolt holes A, B, C, and D. The yield stress of the steel, Fy, and the ultimate stress of the steel, Fu, are also provided. The problem also states to assume the member experiences a fracture failure. In steel design, the design strength of a member equals the resistance factor, B, times the nominal resistance, Rn. For a fracture failure, the resistance factor equals 0.75, and the nominal resistance equals the ultimate stress in the steel times the net area of the steel times U. From the problem statement, we know the ultimate stress in the steel equals 50,000 pounds per square inch. The variable U is the reduction coefficient and is given as 0.80. Therefore, we're left to find the area of steel, A net. The net area of steel equals the thickness of the steel member, T, times the net width of the member, W net. We've been provided the thickness as T equals 0.25 inches. The net width of the member equals the gross width of the member minus the width of the bolt holes plus a term for all diagonal segments along the given failure path. At this point, we'll define 3 failure paths. Path AD will pass through bolt holes A and D as shown. Path ABD will pass through holes A, B, and D, making straight lines between consecutive holes. And path ABC will pass through holes A, B, and C. The path with the smallest net width will govern the design strength of the steel member and be used for the net width in the calculation to find the net area. For path AD, the gross width is the sum of 2.5 inches, 2.5 inches, 4 inches, and 3 inches, which equals 12 inches. The width of the holes equals the number of bolt holes times the width per hole, where the number of bolt holes equals 2 for hole A and hole D. If we take a closer look at a typical bolt hole, the width per hole equals the diameter of the hole plus 2 times the assumed damage thickness along the hole's edge. The problem statement provides the diameter of the bolt hole as 15/16 of an inch, and we've been provided the damage thickness equals 1/32 of an inch. Therefore, the width per hole equals 1 inch, and the width per holes along path AD equals 2 inches squared. Since there are no diagonal lengths along path AD, the third term drops out of the equation, and the net width along path AD equals 10 inches. Next, we'll solve for the width along path ABD. Similar to path AD, the gross width equals 12 inches. And this time, the width through the 3 holes equals 3 inches. So far, these are the same numbers for path ABC as well. For the last term in these equations, S represents the stagger length between the center of bolt holes in a direction parallel to the load P. Variable G is the gauge length between the center of bolt holes in a direction perpendicular to the load P. Since there are 2 diagonal segments in each path, we can write out the quotients, substitute in the appropriate values for S and G, and solve for the net widths for paths ABD and ABC, which equal 9.734 inches and 9.672 inches, respectively. Therefore, the net width in the steel member equals 9.672 inches, and will fracture along path ABC. Solving for the net area, we get 2.418 inches squared. After plugging in the remaining variables, the design strength of the steel member equals 72,540 pounds. When reviewing the possible solutions, the answer is B.